Hello, it's so good to have you here. We're going to be doing some inorganic chemistry, some coordination chemistry. And so what I have here is an octahedral complex. So we're going to imagine that this central atom is a metal, and it is surrounded by 5 of these, what we will call spectator ligands. So they're going to stay bonded to the central metal. So we're calling those L. There's 5 of them. And then we have the leaving ligand, as I'm showing in green, and we're calling that X. It starts out bonded. And then what happens during the course of this reaction is that our leaving ligand dissociates. And we're going to be looking at a dissociative reaction, where first the leaving ligand leaves, and then the incoming ligand Y attaches, giving us the final products, which are the ML5Y, with X having been lost. So this is the overall reaction that we're looking at, and what we're going to do is we are going to propose a mechanism, a reasonable mechanism, of course, and then derive the rate law from that using what's called the steady state approximation. Okay, so let's get going. Put my molecules aside. Okay. Now, with a proposed mechanism, there are various single-step or two-step mechanisms that can be proposed. So this is the one that we're going to work with today. And it is dissociative. And it looks like this. Or step 1 is a fast equilibrium. This is a very common thing that happens in coordination chemistry with ligand exchange reactions, where the starting compound here, and see, I'll put here, this is for dissociative, because this would look different if it were associative. Okay, so what we're looking at is fast equilibrium, where the leaving ligand dissociates and creates this short-lived intermediate. Now, as I said, this is a fast equilibrium, and actually stating which is faster steps, but more importantly, which is the slow steps, is part of a mechanism. So we do want to include that. And since this is step 1, we can say this is the rate constant associated with the forward direction. But there's also a reverse here, and we'll call that K minus 1 in this case. Okay. In this particular mechanism we're proposing, we've got step 2. And in step 2, the intermediate ML5. So notice this only has 5 ligands here. This reacts with incoming ligand Y. And because it's step 2, we have a rate constant. We'll distinguish it from the other ones here by using subscript 2 to go with step 2. This gives us our final product, the substituted octahedral complex. This is our slow step. Okay, this is our rate determining step. Okay. One of the things that is required for a reasonable mechanism is that all of the elementary steps add up to give the net equation. Each of these are elementary steps. Elementary steps are telling us on the molecular scale what exactly is happening with the molecules. Are they breaking apart, like we see here? This step we call unimolecular because there's just one molecule that is reacting. This could be due to thermal effects, so it could be heat that's causing it to break apart. It could be a photon coming in, providing energy for that to happen, to make it over the activation energy for that step. Okay. But in any case, this is unimolecular, one molecule undergoing a change. Step 2 here, this elementary step, we call bimolecular because there are two molecules that are colliding that then cause the change to create something different. And so that's one of the requirements of a good mechanism, is that each of the steps are either unimolecular, bimolecular, or in rare cases, termolecular, where there are 3. Those are more rare, but they're still possible. But you will never see anything more than 3. The probability of 4 molecules colliding is so small that we never see it. So, also with our proposed mechanism, they need to add up to give the net reaction that we're looking at, so we just double check this. And what we see if we add up everything here, we have our starting compound, and we add it with everything over here on the reactant side. And then same with the product side, include everything here. Alright, and then we assess, and we see, we have an intermediate here, we have an intermediate here. Those cancel out, as they should. Intermediates are something that they are produced in one step of a mechanism. And here's our intermediate here. And then it is consumed in a later step, like we see here. This goes away. And ultimately it does not appear in the net equation. Okay, so intermediates appear in one step, and then disappear in a later step. So ultimately, we see here that the net reaction that we would have from this proposed mechanism does indeed match the overall chemical reaction that we're interested in. So that's good. We have met that criterion of what we call a good mechanism. Okay. So now we can write the rate law for the slow step. Because the rate law for the slow step necessarily always must be consistent with the overall rate law for the reaction. Okay? And to add one more thing, the overall rate law for a reaction was experimentally determined. So you can never look at any reaction and immediately right off the top of your head know what the rate law was. There's no way. You have to go into the lab, you have to collect rate data, and then determine what is the rate law. Then you can propose a mechanism. And you can say, all right, what is the rate law for the slow step? And that must be consistent with that overall rate law for the reaction. Okay. So this is where we get to write out what would, for our proposed mechanism here, what would the rate law be for that slow step? And so the way I do this is I write out, okay, for the second step, I'm going to give it a subscript 2. And I'm going to write the rate law for this elementary step. We are allowed to write rate laws directly from elementary steps because the elementary steps are telling us exactly how these species are interacting with each other. And those would affect what the rate is for that step. So elementary steps, we can do this. We can write, here's the form of a rate law. We include the rate constant first for that step, and we look at everything on the reactant side. That is on this side of the arrow, pointing that way. So we can directly write these two molecules that collide. That's our intermediate. And this is the incoming ligand, Y. Okay. So this is, I usually call this a mini rate law. This is for our slow step. But here's the problem. Intermediates are not allowed in an overall rate law. So we can't just say, oh great, we're done. Here's the rate law for the slow step. Because although this might be consistent with the overall rate law, intermediates are not allowed. This is one of our rules. This is one of our stipulations. Not allowed in the overall rate law. Okay. So what do? We must substitute. Okay. So we have to create an equation that allows us to substitute in what is another way that we can express the concentration of the intermediate in terms of products, reactants. As a side note, catalysts are also allowed in the rate law, but we don't have a catalyst here, so we don't need to worry about that. Okay, so this is where we invoke what is called the steady state approximation. This is one of the more comprehensive ways of solving this kind of problem. There is another way that's a little bit simpler, but as I said, this will then encapsulate more scenarios, so to speak, for these kinds of problems. So this is why I teach this in my Inorganic Chemistry class. So there might be some general chemistry classes that introduce this, but also sometimes it's an upper division chemistry class where you learn this. Just depends on where you go to school and where you're studying it. The steady state approximation, this is what it's saying, is that it's making a couple assumptions. Okay, so it assumes that the intermediate, a concentration of the intermediate, is very small. Okay. And it also assumes that the change in the concentration during the reaction is close to zero. So we can also say change, and I'll just call it I, is approximately zero. So during the course of the reaction, you could look at it this way. Here, let me draw a plot. If we were to plot out the concentration of the intermediate, and we're looking at time over the course of the reaction, when the reaction first begins, there's no intermediate. It hasn't had a chance to form. So it would be at zero. But intermediate begins to form, so it goes up, but then it will flatten out. It might even form some and then kind of start going back. But the main point is this stays low and flat. Okay, the concentration is low, it's very small, and the change in the concentration not changing much. And then eventually the reaction ends and this tapers off. Okay, so right in this time frame here, this is where we're making our assumption. Okay, this is where the concentration is in its steady state. Okay, not changing. So our steady state approximation, we just live in this area and we make our assumptions based on that, which is for most of the reaction itself. And that's why this works pretty well. I should say it works very well. It's used all the time. Okay. So now, let's see, what can we do with this? I think it would be helpful, actually, if we can see the mechanism here, and we'll refer to this. Okay. So, here in our mechanism, here are all the ways that the intermediate is formed. Intermediate is formed by starting compound, breaking apart in this direction, and forming it. So what we can do in the steady state approximation is we can say, all right, according to steady state approximation, the change in concentration of the intermediate over time is equal to 0. So we're going to look at all the ways that the intermediate is formed and all the ways that it is consumed. And the one way it's formed, we just acknowledged, is this direction. So we can write the rate law for this elementary step just going in this direction, forming it. Okay, so because it's forming it, that's going to be a positive value. Okay, 1. And it's just by starting material breaking apart. So that's the only compound that will appear there. Okay. Now we look at what are all the ways that the intermediate disappears. Well, we see it disappears here in step 2, going this way. So we can include that, and we'll make this negative. So step 2, ML5 is colliding with Y. But there's another way that the intermediate disappears, and that's this back reaction. See over this arrow here? We have the intermediate could collide with X and reform the starting compound. So here is the other way. Okay, -1. Intermediate collides with X. Okay. So now what we can do, because we have essentially created an equation, so we can solve for the concentration of the intermediate. Okay, so we can do this. These are negative. So put these, let's add these over to this side since it equals 0. So I'll add this over to this side. So it's positive. 5y. Let's add this one. -1. X. And that leaves behind this one. So just leave that one on the right side. And we know it's positive, so I'm just going to drop that positive sign. 1 ML5X. Okay. So now, what's our goal? Our goal is to solve for ML5Y. Wait, sorry, ML5. So we want to isolate ML5Y, which these two are added together, but they each have ML5Y multiplied in them. So we can pull that out. A little bit of algebra. If you remember, factoring. So that leaves behind here K2Y. And here we have factored out ML5. And that leaves we still have K1 ML5X. Okay, make sure I get all that in. Oh, we're so close. We're so close here. Oh, I didn't close the parentheses. Okay. So, because we're trying to solve for ML5Y, we can now, I keep saying Y, I'm so sorry. We're trying to solve for the intermediate ML5. So now what we can do is we can take this, divide both sides by that. We end up with K1 ML5X. I have all this. K2Y plus K minus 1X. Beautiful. Okay, so now you might ask, why did we even do this? This is beautiful, but why? Well, we have to go back. Let's look back here. Let's remind ourselves why we did this. Okay, we're looking back at the rate law for the rate determining step. We wrote it out. Intermediate's not allowed. So we solved for this. And now we can plug that in. Okay, so here, let's rewrite this over here. This is where substitution will occur. Okay, so our slow step rate law. That was rate. It was the second step for our proposed mechanism. So rate 2, K2, here's our ML5, and it was times Y. So now that we have solved for intermediate ML5 in terms of, here we have a reactant, here we have another reactant, there we have a product. All those are allowed in a rate law. So we can now substitute in all of that into here. And that will give us our overall rate law. So I am going to just write rate to acknowledge that now we have arrived. Here's our overall rate law. So, let's see, here's our numerator. Let's write out everything in the numerator. We have a K1, we have a K2, we have our ML5X, and we have our Y. So let's put all those things in the numerator. I like to put the numbers in order, so I'm going to put K1, K2, and then here's our ML5X and our Y. Okay, so that's everything in the numerator. And then now we can have everything in the denominator. K2 or Y and K minus 1 and the X. Whew, we've done it. We've done it. Okay. So here is the overall comprehensive rate law for dissociative ligand exchange reaction. Okay? Oh, goodness. Okay. Morning. All right. Now, one last thing I wanted to mention is what would the rate law simplify to in large quantities of Y? So what if we put in, as the experimentalists, a whole bunch of incoming ligand so that there was an extremely large amount of Y compared to the other compounds that are there, like our starting compound. So, in other words, we could say Y is much, much greater than the starting compound, which means that it is also much, much greater than X. Okay? Because you can only have, at most, as much X is released as there was on the starting compound, because that's where it comes from. So we can take a look at our rate law here, and we see that if Y is much, much greater than X here, then you can actually make an approximation, another approximation, where we can ignore this term here. So, this approximation, again, it works really well for kinetics. So because we can ignore this term, then the rate law becomes K1, K2. The top part is not changed. We still have compound here. We still have it being multiplied by Y. But Y is so much greater than X. Because they're being added together, we can ignore that. So we end up with this rate law. But look at this. Y can now directly cancel out. K2 cancels out too, mathematically. So we end up with this rate law. K1 multiplied by ML5X. We now have simplified enormously to a first order reaction. But because this was created by conditions, by changing the conditions, by just putting in a lot of Y, a lot of the incoming ligands, this is called pseudo first order. First order. So a lot of times, in cases like this, where we know we have a complicated rate law, and we can simplify it by putting in a lot of one of the reactants, we call it pseudo first order conditions. If we're talking with other mechanistic chemists, other kineticists, or if we're doing these kind of problems, putting in lots of Y, pseudo first order conditions, which then give us a pseudo first order rate law. A lot of times we call the rate constant for pseudo first order conditions K observed, because that's the rate constant that you observe in the lab, that you determine experimentally. Okay. It's just a term. Oh goodness. So the main thing is these are rate constants, regardless of what you name them. Okay. And when we're writing out the mechanisms, the rate laws from the mechanisms, we use 1 and 2, -1. Okay, these are from our mini rate laws, but often they just get combined together. In this case, where they're multiplied, as one rate constant, since a constant times a constant gives you another constant. So, alright, I want to make sure that I mentioned pseudo first order since it's so common. We see it a lot with these types of reactions and rate laws, as well as others. So, just as a reminder, everything we just derived is for this specific mechanism. And if you have a different mechanism from this, then your rate law will turn out differently, or could turn out differently, I guess, because you can end up with the same form of rate law with different mechanisms. So that's what makes it really challenging sometimes, right? You can disprove a mechanism, but you can never prove one. There's different rate laws that can correspond to different mechanisms, and it makes it really challenging, but also really fun to do this. I enjoy this a lot. Alright, well, let me know if you have questions, and hopefully this was helpful. Let me know. And let me know if there are other topics you'd like to hear about. I'm always, always happy to take requests and create videos for you. So please subscribe and also hit the bell that's on there. And that alerts you when I upload a new video. Okay, well, thank you so much. And I will see you again very soon.